Continuity, Part 2. Recall that there are three criteria for continuity. F of a has to exist, the limit as x approaches a of f of x has to exist, and the limit and the output have to be equal to each other. But there are actually a couple different types of discontinuities, so cases where one or more of these are not true. A removable discontinuity is a discontinuity where the limit exists at the point. So that means that we have the limit existing, but f of a does not exist. So an example of this would be f of x is equal to x squared minus 1 over x minus 1, because x equals 1 is not in the domain of our function. So that means that f of 1 does not exist. So to check for removable discontinuities for rational functions, we're looking where that denominator does not equal 0. And to see whether this is a removable discontinuity, or as we'll see next, a non-removable discontinuity, that means that we have to check the limit. So we look at the limit as x approaches whatever is not in our domain, so in this case 1, of x squared minus 1 over x minus 1. And we know that x squared minus 1 is a difference of squares and can be factored. So this is equal to the limit as x approaches 1 of x plus 1 times x minus 1 over x minus 1. So our x minus 1s will divide out, and I'm left with the limit as x approaches 1 of x plus 1, which is equal to 2, which I can see using direct substitution. And we can see at this point, so at this x is equal to 1, we have a hole. And a hole is an example of a removable discontinuity. So we have a removable discontinuity at x is equal to 1, because even though f of 1 does not exist, the limit as x approaches 1 of f of x does exist. A non-removable discontinuity is where a limit does not exist at a point. For rational functions, we still need to look at our denominator in order to find x values that make it 0, which means they're not in the domain. So f of 1 does not exist, since we'd have a denominator of 0. And then for rational functions, in order to check their discontinuities if they can't be simplified, or rather check their limits if they can't be simplified, we need to take a look at a graph. And if we look at this, our left limit goes to negative infinity, but our right limit goes to positive infinity. So the limit as x approaches 1 of our function 2 over x minus 1 does not exist. So this is a non-removable discontinuity. In addition to looking at the continuity of rational functions and just graphs of various functions, we also want to look at the continuity of piecewise functions. So that means that we need to be checking for those three criteria. So f of a exists, the limit as x approaches a of f of x exists, and that the limit as x approaches a of f of x is equal to f of a. So we need to check for discontinuities. So if we look at this first piece of our function, this 1 minus x squared is continuous when x is less than or equal to negative 1, or sorry, less than or equal to 1. And that's just something we know about polynomials. Polynomials are actually continuous for all real numbers. And then if we look at the natural log of x, the natural log of x is continuous when x is greater than 1. That's something that we know. So that means that what we need to check are the domains where our functions switch over. So that means that we're checking f of 1. The first thing we need to show is that f of 1 actually exists. If we look here, this is x is less than or equal to 1. So as long as 1 is part of the domain of this function, I'll be okay, because f of 1 will be part of that piece. So I can substitute 1 into my function. So 1 minus 1 squared is 0. So I have a closed point at x is equal to 1. So f of 1 is equal to 0, which means that it does in fact exist. The next thing I need to check is to make sure that the limit as x approaches 1 of f of x exists. So this means that I need to check on either side of 1. I know that my left limit goes to 0, because this is the piece on the left. I need to check my right limit. So I need to substitute 1 into my other piece. So I have the natural log of 1, which is also 0. Oop. And this time I have an open circle because x is just greater than 1. So the limit as x approaches 1 from the left is 0, and the limit as x approaches 1 from the right is also 0. So 1 from the left is equal to 0, and 1 from the right is equal to 0. So my second criteria is true. And now the easier one to check once you find the first two is just making sure your limit and your output are the same. Since the limit as x approaches 1 is equal to 0, which is also equal to f of 1, our third criteria is met. So this function is continuous from negative infinity to infinity. Sometimes our task is to create a continuous function. So here we have a piecewise function. F of x is equal to cx squared minus x if x is less than 2. And our other piece is 3 minus cx if x is greater than or equal to 2. And the question asks for what value of the constant c, meaning it's a number that doesn't change, is the function continuous. So the first thing we need to show is that f of x exists, or f of a exists. So we need to figure out where this might not be continuous. Well, cx squared minus x is a polynomial function, so that's continuous from negative infinity to infinity, so it's definitely continuous when x is less than 2. 3 minus cx is a linear function, so that's continuous from negative infinity to infinity, so continuous if x is greater than or equal to 2. That means that the tricky piece here where I might not have continuity is where my two pieces switch. So that would be at x is equal to 2. So my first task is to show that f of 2 exists. So I need to figure out what f of 2 is. Well, the piece of my domain that includes 2 is this 3 minus cx, because I have x is greater than or equal to 2. So I substitute 2 into my function. So that'll be 3 minus c times 2, so 3 minus 2c. So f of 2 exists. Next up, I need to show that the limit as x approaches 2 of f of x exists. So far, I know that my right limit exists, so the limit as x approaches 2 from the right, since this piece is larger than 2, it'll be from the right. And it's equal to 3 minus 2c. So now I need to look at my left limit. So I look at my other piece. So I have 2. Substituting 2 in, I get c times 2 squared, so 4c minus 2. That's just substituting 2 in for x. So my left limit is 4c minus 2. And in order for this to be continuous, these have to be equal to each other. Well, now I have a little equation that I can solve. So I can add 2 to both sides. So I have 5 minus 2c is equal to 4c. And I can add 2c to both sides. So I have 5 is equal to 6c, which means that c has to be equal to 5/6 in order to make these limits equal to each other. And since I found a value of c that makes these limits equal to each other, and these limits are just the outputs for each piece of my function, I know that the limit as x approaches 2 of f of x has to be equal to f of 2. So c equals 5/6 is the constant that will make f continuous from -infinity to infinity.